where Picard iteration converge but not
Maybe,
Lipschitz is continuous.
maybe I don't know. I don't know as of now if there is any example like that, but as of now it shows what we have shown is that under this condition Picard iterations must converge, and if we drop this condition Picard iterations need not converge.
Okay, sir.
Okay, so for showing the Picard iterations to converge, always it is Lipschitz continuity is required. Without that, it may or may not. We don't have any concrete proof for uh, or examples. Examples, there may be example. I don't know. I have not thought about an example because mathematically it is not required. Because for me, it shows that Lipschitz continuity is there, then the Picard iterations converge. If it is not there, it need not converge.
Okay, sir. And along with these questions, can the solution be unique? तो यहाँ पर यूनिक सोल्यूशन के लिए लिप्सिस कंटिन्यूअस होना पड़ेगा, ऐसा कोई फंक्शन लेना पड़ेगा, है ना?
No, if there is, again, this is the question. The Lipschitz continuity is there, then the solution is unique. Okay, so if Lipschitz continuity is not there, then also it is possible that the solution may be unique. Okay, so that shows
Okay,
that
sir.
Lipschitz continuity is only a sufficient condition for uniqueness, but not necessary condition.
Okay, sir. Clear.
Okay.
Thank you, sir. Yes.
Yeah. And other example, what you see on the screen is that we see that this is an example where you see that the solution is going to be unique, and you see that there exists a solution also. What is the solution? Solution is 0, and 0 is the only solution for this problem. Okay, there is
Yes, sir.
existence and uniqueness in this example, what you are seeing on the screen. Existence is there, uniqueness is there, but the function is not Lipschitz. Okay, but the
Yes,
function
sir.
is not Lipschitz. Okay.
तो जैसे सर इस केस पे कहा कि सर ये लिप्सिस कंडीशन जो है ये मतलब सफिशिएंट है मतलब बट नॉट नेसेसरी, तो सर अभी जो पहला केस था कन्वर्जेंस वाला, तो
Lipschitz continuity is
सफिशिएंट बट नॉट, यस सर, जो हमारा पहला केस है जो कन्वर्जेंस वाला था, तो वहां पे भी हमें नहीं पता कि सफिशिएंट है, सफिशिएंट तो है मतलब बट नेसेसरी है कि नहीं भी कंफर्म नहीं है ना सर.
Yeah, first problem that I gave is that we don't know existence of that, right? So I didn't show whether there exists a solution for that problem, right? We only showed that the function doesn't satisfy the Lipschitz continuity, and therefore, and the corresponding successive approximations or Picard iterations are also not converging. That's what we have seen. Also, the problem has at most one solution, but we don't know whether there exists a solution for that problem or not. Okay, and in this case we are seeing that there exists a solution. 0 is the only solution. 0 is a solution and 0 is the only solution. So that means that without Lipschitz continuity we can get existence and uniqueness. Okay, I'll come back to the first problem, what I said, that is the Muller's example, where you have only the continuity of the function but not Lipschitz continuity of the function. Whether in that case whether there exists a solution is still not clear to us. Of course, I will tell that I will show that that problem has a solution later. Okay.
Okay, sir.
Okay, so there are other simple cases where one can show the uniqueness. Okay, so for example, what we have in for the uniqueness is suppose uniqueness means that there is at most one solution. That's what it means. Whether there is a solution or not, if at all there is a solution, there is only one solution. That's what it means by uniqueness. It doesn't guarantee the solution. Uniqueness doesn't guarantee the solution. The solution is guaranteed by existence. Okay. So what we assumed is the Lipschitz continuous function, right? So suppose we have a function. Okay. Suppose if so I'm writing only the variable x, not the t of x, is just a continuous function, is just a continuous, not Lipschitz. not Lipschitz. Okay. And this function fx is strictly positive in the whole of R. In the whole of R. Then the initial value problem, if you take x prime equals to fx. Okay. So x at point tau equals to xi. This has a unique solution. This has unique solution. Okay. For example, what are the kind of examples that you will have is, for example, if I take fx, which is equals to 1 plus x to the power of 2 by 3. So this function is strictly positive in the whole of R. And it is not Lipschitz in around 0. And this is not Lipschitz around 0. So if I take exactly the problem x prime equals to, so if I take the problem x prime equals to this with x at 0 is 0. Okay. Then this problem will have unique solution because of this. And existence, we don't know yet. Okay. We showed so far existence only for the non-linearity, which is Lipschitz. Okay. So why the uniqueness comes? So look at you define the function f like this. So fx, which is equals to tau plus xi to x ds by fs. Okay. Then we see that f prime, if I write f prime x, okay, which is going to be 1 by fx, which is strictly positive. Therefore, by a theorem which is called inverse function theorem in the real analysis, it shows that f is invertible 1 1 and onto. F is 1 1 onto, and f inverse is differentiable. So this is a consequence of a theorem called inverse function theorem. It's basically what the inverse function theorem tells is that if I take a function, okay, any function, say if I take any function like this, I want to know where I can write the inverse of this function, and this inverse of this function is also a nicely differentiable function. Okay. So if I take the point, say at this point, okay, so here I can write, because this function is, you can see that this is a nice function which is defined here with respect to y-axis. So therefore inverse of this function is defined, it is 1 1 and onto. But if I take this point, it is not, because you take any neighborhood of this point, there are two branches which are coming here, right? Therefore, what is the difference between this point and this point? At this point the derivative is 0, and at this point the derivative is going to be either positive or negative. It is not 0. So that's what the inverse function theorem generally says, that if more general thing is about multivariable calculus, but in one variable calculus it says that if the derivative is non-zero, the function is 1 1 onto, and f inverse is defined, well defined, and that is also a differentiable function. Okay, so let us take the, let phi be the inverse. Phi is inverse. And we can write the domain of phi, which is phi maybe from, you can write a minus to a plus, a domain where this to, right, so to R, where this a minus is the limit of f as x goes to minus infinity, and this can be the limit of f where x goes to plus infinity. They can be, I mean, limit can approach to infinity also. So like that we define. Then you see that phi is a solution. Phi is a solution. Why is that phi is a solution? You can check that phi is phi of t, right? So phi of say tau is going to be f inverse of tau, which is xi, right? So from the definition, f inverse of tau is going to be, right? So f of xi equals to tau. See here, if I take x equals to xi, I'm going to get tau. Therefore, f inverse of tau is going to be xi. So the initial condition is satisfied. Look at what is the derivative, f prime. F prime by the inverse function, it is going to be 1 upon f prime of f inverse t. I guess you know how to see this derivative, and this is nothing but f of I. Right, so I guess you can see this. That's what I said. So you write f of phi is going to be t, right? So how to do these things, I guess you know. F of phi is going to be t because it's phi is inverse of f of phi t. So now you differentiate this, right? So you get f prime of phi into phi prime is 1. Therefore, phi prime equals to 1 upon f prime of phi. And what is phi? Phi is nothing but f prime of f inverse. So that is what is this step. And right. And what is f prime? F prime, you know, from the definition. So from the definition here, what is f prime? F prime equals to 1 by f. So f prime of phi is going to be 1 by f of phi. 1 by f of phi. Right. So we know that phi prime is what we wrote. F prime of phi is 1 of f of phi. Therefore, phi prime is 1 upon, right? Phi prime is 1 upon f prime phi. Right? So this is nothing but f of phi. Right? Therefore, phi prime equals to f of phi. That's what we have. So it's the solution. Now we claim that phi is the only solution. Suppose xi is another solution. So what is the meaning of xi being another solution? It means that xi prime
Xi also satisfy
f of xi. Yeah. Right. So that means 1 is equals to xi prime by f of xi. And if you see what is this one, this is going to be, on the other hand, compute what is f of xi whole prime. This is going to be f prime of xi into xi prime. Okay, and that is nothing but xi prime by small f of xi. So therefore, this is equals to this. Xi prime by f of xi is equals to this. So I can now ignore this. Now integrate. So integrating this, we get f of xi equals to t plus c. Now take t equals to tau. T equals to tau to get f of xi of tau equals to tau plus. Okay, what is xi tau? Xi at tau is to be, right? So it's the solution means xi at tau equals to xi, right? That's the meaning of solution. So xi at tau is going to be psi. So this is f of psi, and we know that f of psi is equals to tau from the definition. So this implies c equals to 0. Therefore, you have t equals to f of psi. Right? So this implies t equals to f of psi. Okay, but this is same as f of phi. Why? F of f and phi are inverse of each other. Therefore, f of phi is nothing but t. So t equals to this and t equals to this, and f is 1, 1 and on 2. So this implies psi equals to phi because f is 1, 1. So if there is any other solution, okay, solution means that it satisfies the initial value problem. So from that we have this relation psi prime by f equals to 1, which is f of psi whole prime. Integrating it, we get this. Just substituting the initial value, we see that t equals to f of psi. Okay, but we know that f and phi are the inverse of each other. Therefore, t is nothing but equals to this, and f is 1 to 1 implies phi equals to 0. So the uniqueness actually can be shown without using the Lipschitz continuity. Lipschitz continuity, of course, is a very easy tool to show the uniqueness, but otherwise there are ways from the analysis, from the real analysis techniques. So in the previous class I showed the uniqueness of the Muller's example using the mean value theorem. Okay, now we are seeing that using the inverse function theorem. So the uniqueness can be shown, otherwise also that's what we have seen. So if we can show the existence also by otherwise means that by not using the Lipschitz continuity, okay, then we will be having a better understanding of initial value problems. Okay, so that is the Peano's theorem. I'll do it a little later. So what the Peano's theorem says is if x prime equals to ftx, okay, and x at t naught equals to x naught. So if f is continuous, okay, in a rectangle around this, around t naught, okay, around t naught and x naught, then there exists a solution. The solution exists, but it doesn't say anything about the uniqueness. That's the, if f is continuous, see the continuous in two variables. If f is continuous, yes, there exists a solution. Therefore, using this Peano's theorem, we can say that the Muller's example, okay, that also has a solution. That also has a solution. And in the previous where we showed the uniqueness, where we assumed that f is just a simply continuous function, need not be Lipschitz, that also has a solution. That means in this case also existence is guaranteed by, Peano's theorem. So you have the existence and uniqueness even without f satisfying the Lipschitz condition. Okay. So let us, I will, for proving this Peano's theorem, I need some elements of metric spaces. So before going to that, let me do something more about from the local solutions to the global solution. So what is the meaning of local solution? So the local solution, I mean to say, the solution exists in a small interval. Okay, solution exists in around, okay, in a neighborhood, in an interval around the initial point. So that is the local solution. And what is the global solution? So the global solution means solution exists everywhere. Everywhere means that it can be it can be the whole real line. Yeah, the whole real line. It can be the whole real line, or if our function f is defined only in a small interval, then in that interval. Okay, it can be x prime equals to f dx. Okay, where f is defined on an interval, say AC cross R to R. So if the solution exists in the entire interval, so T naught is a point belong to this, right? T naught belongs to the AC. So if the solution exists in the entire interval AC, then we call it as a global solution. Okay. Or if f is, it's only, I said, an interval, so it can be the whole real line also. So I already said one place where you look at a global solution, where you get a solution for all R, for the entire AC. That is, if we have f to be, right? So if global solution, so if f is from R cross R, okay, to R is Lipschitz. So in this case, it is not locally Lipschitz, it is globally Lipschitz. Lipschitz in the whole of R. Whole R. Or you can write R cross R because we are keeping the T as a silent variable for the Lipschitz continuity. We are looking at Lipschitz continuity only in the second variable, but the function is defined in the R cross R. Then solution exists in the whole of R. Okay, so in this case, you can see what we saw in this is that is going to be minimum of a comma b by m. Okay, so a is infinity here, and b is also infinity. So you can take both of them to be infinity. Therefore, minimum is going to be infinity. So the solution exists everywhere. That is the global solution. So if it is not a global solution, okay, then what is the maximal interval? If solution is not a global solution, okay, then what can we say about maximal interval? What can we say about maximal interval? Maximal interval of existence. Okay, first we will see that this is definitely not a maximal interval of existence. Let's see how this is not a maximal interval of existence, and then we have to see what can we say about the maximal interval of existence. So let us look at a simple example. X prime equals to x square with say x at t naught equals to x naught, which is non-zero. Okay, so you can compute the solution for this. You can see that xt by separation of variables minus 1 by t minus t naught minus 1 by x. So this becomes a solution. Okay. Therefore, it has a singularity. Okay. So the solution is defined. Okay, so the solution is defined. Solution is defined for t less than t naught plus 1 by x naught for all t. Right? For all t less than this, the solution is defined. Of course, if x naught is positive. Otherwise, we take the other branch. Okay, so we assume that x naught is positive. And let us look at what the Picard's theorem H says. What is the H? What do we get from Picard's theorem? So what we had there is the H, right? H is the minimum of A, comma B by M. So we have to find what the A and what the M is, right? So take A to be A and B, take any rectangle R around the T naught X naught. So R be the points Tx where mod T minus T naught is less than or equals to A and mod minus X naught less than or equals to A. So on this rectangle, I have to find what is M. Yeah, so M is of the function x square or R. So if x belongs to R, then we know that x is mod x minus x naught is less than or equals to B, right? X belongs to R implies mod x minus x naught is less than B. So that means that x is going to be less than B plus x naught, right? So therefore, this is going to be less than or equals to B plus x naught square. This is an estimate. Therefore, H becomes the minimum of A B by B plus x naught whole square. We are taking x naught to be positive. Similar calculations can be done for x naught is negative. Right. So now we have to see the set of all values of A and B for which this H is maximum. Okay. We have to see the all values of A and B for which H is maximum. So since I am looking at H is maximum and this is only minimum of A and B, so we need to allow the maximum coming out of this A and B by B plus x naught square. Since x naught is positive, B by B plus x naught is going to be less than 1. Okay. Therefore, first of all, let me choose A to be greater than 1. If I choose A to be greater than 1, then H is going to be the minimum value of B by, then H is going to be the maximum value of whatever is the maximum value of B by
B x
naught
square.
Right. So the maximum value of this. So you can write the maximum value of this by writing a function x by x plus x naught square and then differentiate it, and then you will see that this is going to be 1 by 4 x naught. So that means the solution is solution according to this the theorem that we compute h. Okay. According to the h, the solution is defined for x naught defined for what is that 2 in a t naught plus 1 by 4 x naught. But this is something which is strictly less than t naught plus 1 by x naught, right?
Yes.
Yeah. So that means that what we are getting from the Picard's theorem clearly shows that whatever is ensured in the Picard's theorem, that you have only the solution in this domain. Okay, solution exists only in this domain. That is not a maximal domain. That is not a maximal domain, right? So what can we say about the maximal domain? So that's what the theorem we have here. So what we can say about the maximal interval of existence. Okay, so if f is defined, okay, defined in the whole R2. Okay. But it is only ellipsis continuous in a neighborhood around the initial value. Okay, it is not Lipschitz, but it is defined everywhere, but locally Lipschitz around initial value. Okay, then so if I call J to be the if J is the maximal interval of existence, okay, then J is open interval. Okay, J is an open interval, or you can say J is not a closed interval. Open, let me not say open interval, but because for solution anyway it has to be interval, so it's fine. Okay, maximal interval of existence. So the J is open intervals. J cannot be a closed interval. That's what we are seeing also here in this particular example. You have the solution which is defined for all t less than this. It is not defined for t equals to this, right? So it's an open interval. Right. So how do we show this? Suppose x naught is a solution, and okay, suppose by contradiction we assume that it is a closed interval. X naught t is a solution, and and alpha beta is the maximal interval. We have to get a contradiction, right? So we have to get some contradiction. Suppose this such a closed interval is there, right? Then what we can do is that x naught t is defined at beta, right? So x naught t is defined at beta, So let us call it to be x naught beta. Okay, x naught beta. Let us call it to be x naught beta. Okay, so that is we have an interval, okay, alpha beta, and you started with a point say t naught, and you have a solution. So it is there up to here. So at the end point. So at the end point, again you consider the initial value problem. So at beta, consider the problem. Consider the initial value problem. So x prime equals to f dx, okay, and x naught x at beta equals to x naught beta. So again there is there exists an interval around this point beta. Okay, around beta. So let me call that interval to be beta plus delta to beta minus delta for existence. So let me call this as x beta. Let me call this as x beta. Then we define the new function, say x2. So now let us define a new function, say y. So yt, which is going to be the first xt for alpha beta, and beta plus delta, beta minus delta. So beta minus delta to beta plus delta. So define this to be x beta. Then yt is a solution of the Snell problem. Okay, so then yt you can write if alpha beta, or you can write t naught to beta. Then yt is a solution of x prime equals to f with x at t naught equals to x. But what we assumed earlier was alpha beta is the maximal interval. But here we got alpha to beta plus delta. So that is not a maximal interval. So that's a contradiction. Okay. So it is not difficult to show that this is a solution. And so that you can write what is the left derivative and right derivative at the point beta. Okay, because there is a solution now x beta, the left derivative comes from the xt and y derivative of y comes from the x beta.
So what is x beta t?
X beta t is the solution that you have here. So this is my x, right? And this is beta plus delta. So this is again satisfies an initial value, right? So you tie this initial value, this solution here. So this has a solution from here.
सर इसको इस तरह से डिफाइन कैसे कर सकते हैं, मतलब टी नोट टू बीटा एंड बीटा माइनस डेल्टा, सो दिस बोथ आर कोलैप्सिंग देयर.
Here?
Yes, sir.
Yes, sir.
Just define.
Yes.
It is just defined, no? What is the problem in defining? I'm defining it, right? xt, which you already have, which is coming from the, which we assume that it is a solution, right? Let xt be a solution, right? This is what x naught t, sorry, x naught t.
Yes, sir. No problem.
So take it to be the x naught t, right? X naught t is already there from alpha to beta, and from
yes,
beta to beta plus delta, right? So you write beta to beta plus delta. Don't write beta minus
yes,
delta.
Yes, sir. Yes.
Beta to beta plus
now.
delta you define to be x beta.
Now.
Okay. Yeah.
Yes.
So you are basically tying these two. This is one solution, and you tie that solution with other one. And then you have to show that it is actually because at both the points this is also solution, satisfies the equation. This also satisfies the equation. Only at this point, right? At this point, if you show that it is a differentiable function, then you have everything. So you have to show that the y is actually a differentiable function. So to show that y is a differentiable function, compute the left derivative and right derivative. So if you compute the left derivative, it is going to be the left derivative, the derivative of x naught prime, right? So that is going to be f of f beta into x naught beta, and you look at the right derivative, that is going to be f of beta to x1 beta, right? So that is both these things are same, because at this point both these functions are same, equal. So therefore y is differentiable function and satisfies this, right? These things we can calculate, I guess, no? Like left derivative, right derivative. Write the definition of left derivative of y. Okay. That is going to be x naught beta minus x naught of beta minus h by h. So that is nothing but x naught prime at beta. You know that it is a solution, therefore, so you can write this. So what is what I mean, that is the one consequence, right? So one consequence of we'll see the consequence of this, but one assertion that what we can say is the maximal interval of existence is an open interval. It cannot be a closed interval. Okay, so what is the consequence of this? So if I say that one consequence is that if xt, which is solution, is bounded, okay, and monotone function, okay, right, and if tx, of course, you need to have need not be a ellipsis function, but it can be a continuous function in whole of R2. Okay, then the solution exists globally. Why is that? It is because you know the fact that bounded monotone functions has limit. Okay, so right, therefore the solution exists everywhere in the whole real line. For example, take the function x prime equals to a function f x t by 1 plus mod f x t. Need not take mod f x t. You can take f to be a positive function, so this is enough. Right, so all other cases you can write yourself. So f to be a positive function. Okay, with x at 0 to be x naught. So in this case, you know, you can see that since f is positive, x prime is strictly positive. Okay, so it is a monotone function. Right, and moreover, x prime, mod x prime is less than 1. Right, mod x prime is less than 1. Therefore, what does this say? This says that the x, okay, is a function which has a slope which is always less than 1. So that means that the function cannot blow up at a point. Okay, and the slope is always less than 1. Mod x prime is less than 1 means it lies between these two, right? It has to be below these two things. Therefore, this implies that x is bounded. Right, so it doesn't have a finite blow up at any finite t, means that x is a bounded function, and x is monotone, which comes from this equation. X prime is positive and x is a monotone function. Therefore, for such a problem, the solution exists globally. So solution exists globally for all t. Okay, so this is how one can use some basic analysis to ensure whether a given initial value problem has a solution or unique solution, or you can say whether what could be the maximal interval of existence. So you need to know the maximal time until you have a solution. For example, you take any paint, for example, paint you are putting on the paint, say hair dye. You put the paint on the hair. You want to know how far it is going to stay. Yeah.
Sir, mod x dash less than 1 implies x is bounded.
Yeah, because slope is always less than 1, right? So for this function, slope is less than 1. So if it is not bounded, if x is not bounded, means what? It is not bounded means that there is a point where it actually goes to infinity or minus infinity, right? So if it goes to infinity, how it goes to infinity? So it goes like this. That means the slope cannot be less than 1, right?
Yes, sir. Yes, sir.
That means the slope cannot be less than 1.
But sir, if fx equal to x by 2, then f dash x equal to 1 by 2, which is less than 1, but fx is not bounded.
That's why I said f is greater than 0, right? It has to be greater than 0 everywhere. Otherwise, this denominator is not defined at some points, you see. You need the monotonicity also, no? Either f is strictly positive or f is strictly negative in the whole real line. Okay? Right. So this is
yes.
About, yeah. So I will stop it here. Next class we will look at something about what are the other things that are required other than the existence and uniqueness for a problem to be called a nice problem, that is called well-posedness. So I will see that, I will show that in the next class. If you have any questions, you can ask me. We have just 2-3 minutes time.
सर जो कल आपने क्वेश्चंस करवाए थे, मतलब जिनका सॉल्यूशन, जिनके एग्जांपल्स आपने दिए थे, आपने कहा था कि वो जो नोट्स में अवेलेबल, मतलब नोट्स में नहीं है वो चीज़ें, तो आप उसको कब तक प्रोवाइड करा देंगे?
It's only one example which is not there, right? The example of Muller, right? Muller example is not there, but everything else is there.
Muller.
Yeah.
Yes, sir.
Only this example is not there. I will say there are still some typos which I am correcting it. So once if I finish the lectures, then I will have all the corrections. I don't want to share too many times. So that's why I shared it before, so that you read that and then also attend the lectures. If there are some errors, then I correct them during the lecture. And then I will, at the end of the lectures, I will give the fresh notes, which is possibly error free. Okay.
Okay, sir.
Yeah.
Sir?
Yes.
So syllabus of quiz will be till Friday